You are standing in a dark control room, listening to a thin radio whisper from beyond every planet you have ever seen. Voyager 2 is the size of a desk, older than the home computers that came after it, and still somehow alive out there in the black. If this little craft loses its balance for even a moment, humanity could lose one of its only working ears in interstellar space. And that is where tonight's story begins. Subscribe here, and each week you get another deep space mystery turned into plain English before the signal fades. The danger does not look like movie danger. There is no fireball, no giant engine burn, no astronaut gripping a seat. The danger is smaller than that, and in a strange way more frightening. It lives in tiny fuel lines, old heaters, slow radio commands, and a machine that must keep a dish pointed at Earth with almost absurd precision while drifting more than 13 billion miles away. That is what makes Voyager 2 so unsettling to think about. The older it gets, the less room it has for mistakes. A lost watt matters. A missed pulse matters. A drifting guide star matters. And when engineers try to save it, the rescue itself can become the thing that nearly kills it. So the real story is not about one dramatic moment. It is about how a spacecraft built in the 1970s keeps walking a tightrope in the cold between stars. To see why this matters, we need to step back now. Most people think Voyager 2's dangerous maneuvers are all behind it. They think the hard part was launch, or the giant planet flybys, or that famous close pass by Neptune in 1989. After that, the usual picture is simple. Voyager 2 just coasts, quietly, passively, like a bottle on a dark ocean. That picture feels right because Voyager 2 belongs to another age. It launched on August 20th, 1977, when the world still heard music on tapes, when screens were small and heavy, and when the outer planets still felt half mythical. It was built by NASA's Jet Propulsion Laboratory, or JPL, in Southern California. It was not sent out to live forever. It was sent to do a job, visit the giant planets, and report back before age caught it. And the job it did was astonishing. Voyager 2 flew past Jupiter on July 9, 1979. It passed Saturn on August 25, 1981. It swept by Uranus on January 24, 1986, and Neptune on August 25, 1989. No other spacecraft has visited all 4 giant planets up close. Even now, that sounds almost impossible. One machine, 4 worlds, a grand tour across a solar system that still felt larger than anyone could hold in their head. When people remember Voyager 2, they usually remember the pictures. Blue Neptune, pale Uranus, storms, rings, moons, strange light. That makes sense. Pictures stick. They hang in the mind like posters. But after Neptune, the cameras were shut down to save power, and the mission changed its personality. It stopped being the spacecraft of glowing postcards and became something quieter, stranger, and easier to forget. After 1989, Voyager 2 did not stop moving. It entered a new life. The mission was renamed the Voyager Interstellar Mission. That sounds grand, but in public memory, it almost vanished. A craft with no fresh planet pictures does not make many headlines. It becomes background hum. People hear that it is still out there and nod politely, as if they are hearing about an old lighthouse still running on a distant coast. But Voyager 2 is not a drifting bottle. It is a balancing act. To talk to Earth, the spacecraft has to keep its antenna aimed home. To do that, it makes tiny turns. Engineers talk about pitch, yaw, and roll. In plain English, that means up and down, left and right, and spinning like a slow record. Roll matters because Voyager uses a guide star, and if that star slides out of view, the spacecraft can lose the reference it needs to stay oriented. That is a strange thought. A machine older than many grandparents is out beyond the heliosphere, the sun's protective bubble of particles and magnetic fields, and it still has to keep looking at a star to know which way it is facing. A small error there can grow into a bigger one. The antenna drifts, the signal weakens, commands become harder. Science can stop, not with a bang, but with silence. And the silence comes slowly. Radio commands do not reach Voyager 2 in seconds, they crawl across space. NASA says it takes about 19.5 hours for a signal from Earth to reach Voyager 2, then another 19.5 hours, roughly, for the answer to come back. Every choice is delayed, every test is remote, every mistake is old news by the time you find out it happened. That alone would be hard enough. But Voyager 2 also runs on a radioisotope thermoelectric generator, or RTG, a device that turns the heat from decaying plutonium into electricity. It loses about 4 watts of power every year. 4 watts is not much in a house. It is a small light bulb. On Voyager 2, 4 watts can be the difference between keeping a heater on or letting a line get too cold. So the mission team has spent years trimming, choosing, and sacrificing. Instruments that once revealed new worlds have gone dark. Some were turned off long ago because the planetary tour ended. Others were shut down because the spacecraft needed to stay alive more than it needed to keep every sensor running. In September 2024, NASA turned off Voyager 2's plasma science instrument to save power. In March 2025, it shut down Voyager 2's low-energy charged particle instrument, called LECP. That LECP shutdown tells you how old Voyager 2 really is. NASA explained that part of the instrument used a rotating platform, powered by a stepper motor that pulsed at 15.7 watts every 192 seconds. The motor had been tested for 500,000 steps back in the mission's early days. By the time engineers planned to switch it off on Voyager 2, it had completed more than 8.5 million steps. That is not old. That is almost mythic. Think about that in ordinary life. Imagine a fan in your house built for one summer, still turning nearly 50 years later. Imagine a flashlight battery that got weaker every year, but the flashlight still had to aim itself at one exact window on Earth. That is the kind of life Voyager 2 lives. Nothing about it is passive. Even surviving is work. This is why people underestimate the spacecraft. The old drama is easy to see. Launch towers shake. Planet flybys fill television screens. But maintenance is hidden. Quiet engineering rarely becomes legend. The public sees deep space as a cold emptiness after the adventure is over. The engineers see a machine that must be persuaded, protected, and sometimes gently tricked into one more year of life. NASA's Suzanne Dodd, the Voyager project manager at JPL, put the spirit of it simply in a 2025 update. She called the Voyagers deep space rock stars, and said the team wants to keep them that way as long as possible. Patrick Kane, the Voyager program scientist at NASA headquarters, said every bit of extra data from the probes is valuable bonus science and a testament to the engineering that began nearly 50 years ago and still continues. That engineering is the real stage for this story. Not a launch pad, not a planet. A machine wrapped in foil and memory, running on shrinking power, nudging itself by fractions, listening to particles and plasma in a place no repair mission will ever reach. By November 25, 2018, Voyager 2 had entered interstellar space, the region beyond the heliosphere. No human-made spacecraft had done that before, except its twin, Voyager 1. So by the time most people think about Voyager 2 at all, they tend to believe the same simple thing. The dangerous part is over. The craft did the heroic work decades ago. Now it is just drifting outward, tired but safe, collecting whatever data happens to pass by. That assumption feels calm. It feels sensible. It also hides where the real danger has moved. But that picture is about to change. The farther Voyager 2 goes, the more the threat shifts from giant celestial encounters to tiny failures inside the spacecraft itself. The old assumption breaks, not with a crash, but with a question. What if the hardest maneuver for a machine this old is not one it made near a planet, but one it must make now, with fading power and no second chance? Write the moment your own assumption cracked in the comments. That simple note helps shape which hidden space stories we unravel next, because it shows exactly where the mystery grabbed hold. The warning signs did not arrive all at once. They came like creaks in an old house. In 2019, Voyager 2's aging attitude control thrusters were having trouble. Engineers expected those thrusters to keep doing the quiet work of pointing the antenna at Earth. Instead, the system needed an increasing and, in NASA's words, untenable number of pulses. The surprise was not loud. It was more like learning that the brakes on an old bicycle now need 3 squeezes where one used to do the job. That forced a bold move. On July 8, 2019, Voyager 2 successfully fired up its trajectory correction maneuver thrusters. Those thrusters had last been used during the Neptune encounter in 1989. The expectation was simple. Old hardware, sleeping for decades, should be treated with caution. The reality was stranger. A set of thrusters built for planet flyby course changes had to take over routine pointing duties in deep space. It was like waking a retired sprinter and asking it to become your balance coach. That was not even the first time the mission had reached back into its own past for survival. JPL reported years earlier that Voyager 2 had switched to a backup set of roll thrusters to save power by turning off a heater needed for the primary roll thrusters. That change mattered because heaters cost energy, and energy was vanishing year by year. The expected path was steady decline. What engineers actually did was more creative. They kept opening old drawers inside the spacecraft and finding one more usable tool. That pattern is important. Voyager 2 survives by turning old design features into new lifelines. What was built as backup becomes primary. What was meant for one stage of the mission gets reused for another. The spacecraft is not just enduring, it is being reimagined from the ground, except the ground is Earth, and the machine is more than 13 billion miles away. Every rescue is part engineering and part archaeology. Then power cuts began to tighten the story. In September 2024, Voyager 2's plasma science instrument was turned off to save power. NASA said the instrument had gathered only limited data in recent years because of its orientation relative to the way plasma flowed in interstellar space. The expectation was that every remaining instrument was too precious to lose. The reality was harsher. Some tools had to go dark so the spacecraft itself could live. It was like taking books off a sinking shelf to keep the shelf from collapsing. The next sacrifice came on March 24, 2025, when Voyager 2's low-energy charged particle instrument was shut down. That instrument measured ions, electrons, and cosmic rays from both our solar system and the galaxy. It also used that power-hungry rotating platform. The expected picture was graceful aging. What engineers found was a machine whose remaining watts had become so important that even a deeply useful instrument could no longer justify its cost. The surprise landed with the force of household math. One old motor had become a luxury. After those cuts, Voyager 2 was down to a smaller scientific voice. NASA's updated instrument status in April 2026 showed two key instruments still operating on Voyager 2 for the foreseeable future: the magnetometer, which measures magnetic fields, and the plasma wave subsystem, which listens to waves in plasma, the electrically charged gas that fills much of space. Expected, a worn-out relic. Actual, a stripped-down interstellar lab. It is like a grand orchestra reduced to a violin and a drum, still somehow playing the song. And while power shrank, another problem loomed on Earth. From May 4, 2025 through February 2026, Deep Space Station 43 in Canberra, Australia, went offline for major upgrades, with only brief windows of operation during that period. NASA's Deep Space Network has stations around the world, but JPL said DSS-43 is the only dish with enough signal power to send commands to the Voyagers. That fact changes the emotional scale of the whole mission. A spacecraft past the planets can depend on one giant ear on one continent. So now imagine the pressure. You are caring for a spacecraft that replies almost a day later. You are watching its power margin shrink. Some thrusters are aging. Fuel tubes can build up residue, a kind of clogging that makes firing less reliable. And the one Earth antenna strong enough to command the craft is entering a long period of downtime. In a story like that, every test begins to feel less like routine maintenance and more like remote heart surgery. The clearest glimpse of that danger came through Voyager 1, Voyager 2's twin. In a May 2025 JPL update, engineers described how they revived a set of Voyager 1 thrusters that had been considered inoperable since 2004. The mission manager, Kareem Badarudin, and propulsion lead Todd Barber explained just how delicate the fix was. If the spacecraft's star tracker drifted too far during the process, dormant roll thrusters might fire while their heaters were still off, and that could trigger a small explosion. That is the kind of sentence that changes how you think about old spacecraft. The expected danger in spaceflight is giant motion, rocket flames, planetary gravity, impact. But here the real danger sat inside a tiny heater circuit and a narrow timing window. The surprise was scale. Something smaller than a coffee maker part could threaten a mission that had crossed the whole solar system. Space often does that. It shrinks the physical cause and multiplies the consequence. Why bring up Voyager 1 in a story about Voyager 2? Because the twins teach the same lesson. The systems are similar. The risks rhyme. The engineering choices echo back and forth. When one Voyager reveals a new weakness, the other suddenly looks more fragile too. These spacecraft are no longer just explorers. They are case studies in extreme old age, under conditions no one can fully rehearse on Earth. Then came another warning. On February 27, 2026, during a routine planned roll maneuver on Voyager 1, NASA said the spacecraft's power levels fell unexpectedly. Engineers knew that any further drop could trigger the undervoltage fault protection system, which would automatically shut down components to protect the craft. That sounds safe, but in a ship this old and distant, automatic protection can start a long, risky recovery. Expected, routine roll. Actual, a near miss. It was like flicking a light switch and hearing the whole house groan. That pushed the team toward a more ambitious idea. NASA called it the Big Bang. The name sounds dramatic, but the goal was practical. Engineers wanted to swap out a group of powered devices all at once, turning some things off and replacing them with lower power alternatives so the spacecraft could stay warm enough and keep returning data. It was not about making Voyager 2 stronger. It was about making it just efficient enough to avoid dying soon. And here is where Voyager 2 became central. In April 2026, NASA said the team planned to implement the Big Bang on Voyager 2 first. The reason was blunt and revealing. Voyager 2 had a little more power to spare, and it was closer to Earth, making it the safer test subject. Tests were planned for May and June 2026. That is a sentence full of tension. Safer does not mean safe. It means if something goes wrong, this is the one you are more willing to risk. Now we can finally name the strange truth hiding under the title. The dangerous maneuver was not a huge burn in open space. It was the act of reconfiguring life support for a half-century-old robot that cannot be touched, cannot be repaired, and cannot be rushed. Expected. A maneuver means motion through space. Actual. A maneuver can mean surgery on power, heat, and pointing. The feeling is different, but not smaller. It is like changing a heart valve by mailing instructions to the patient from another planet. And still, there is uncertainty here. Even the people studying these systems do not claim neat control over every detail. JPL has described residue building up in thruster fuel tubes. Engineers know power margins are razor thin. They know heaters matter because frozen fuel lines could end operations. But no one on Earth has a perfect handbook for a 1977 spacecraft in interstellar space after nearly 50 years. That hesitation matters. It keeps the story honest. Todd Barber called the revival of long-dead thrusters on Voyager 1 a miracle save. Kareem Badarudin explained that earlier teams had accepted some failures because they did not expect the mission to last another 20 years. That is one of the most moving things about Voyager. Its biggest challenges come partly from its own success. It outlived the assumptions built into it. The spacecraft is now old enough to find bugs in human optimism, and yet the science still matters. Linda Spilker, Voyager project scientist at JPL, said every day could be the mission's last, but that any day could also bring another interstellar revelation. That is not sentimental language. It is a precise statement of value. Voyager 2 is still measuring magnetic fields and plasma waves in a region no other craft has explored. It is not repeating history. It is making unique measurements in real time, right now. That is easy to miss because the data do not look cinematic. They look like lines, counts, waves, and fields. But those measurements tell us what the space between stars is like, just outside the sun's bubble. Voyager 2 helps show that the heliosphere, our solar system's protective bubble, is not perfectly round. Think about that. A probe launched when disco was new has helped reveal the shape of the invisible border that wraps around our cosmic neighborhood. Bring it down to Earth for a second. When your phone battery dips into the red, you close apps, dim the screen, and hope it lasts until you get home. NASA is doing a version of that with Voyager 2, except the phone is older than many cities' subway maps, the charger does not exist, and home is more than 19 hours away at the speed of light. The domestic feeling is familiar, the scale is not. So the reveal is bigger than one spacecraft problem. Voyager 2 teaches that the late life of a mission can be more dangerous than its famous youth. The great planetary flybys were spectacular, but they happened when the craft was younger, warmer, and better supplied. What threatens Voyager 2 now are tiny margins. A few watts, a clogged line, a heater, a roll, a delayed command. The farther it goes, the more survival itself becomes the maneuver. And here is where this stops being about one machine and begins being about us. If the reveal in this story is right, then the way we think about exploration has to quietly shift. Heroic moments are not only the loud ones at the beginning. Sometimes the deepest bravery is patient, careful, technical, and almost invisible. Sometimes history is held open by people who spend weeks saving fractions of power on a machine most of the world stopped watching years ago. Pass this story to one older skeptic or one younger learner who thinks space missions end when the headlines do. Sharing it with exactly that kind of person matters, because it turns a forgotten signal into a living conversation across generations. What changes now is not just Voyager 2's schedule, it changes the meaning of endurance in space. NASA believes that with careful power conservation, the two Voyager probes could continue operating with at least one science instrument into the 2030s. That is a staggering sentence. It means a machine launched in 1977 may still be doing science when it is more than 50 years old, in a place no other probe has reached. But the future gets narrower as the calendar moves forward. On the instrument status update posted April 17, 2026, Voyager 2 still had its cosmic ray subsystem on, while its magnetometer and plasma wave instruments remained active, and its low-energy charged particle instrument and plasma science instrument were already off. NASA also said Voyager 2's cosmic ray subsystem was scheduled to be shut off in 2026. That means each remaining channel of information now sits on a clock. The Big Bang work makes that clock especially important. In April 2026, NASA said tests on Voyager 2 were planned for May and June 2026 because it had slightly more power and sat closer to Earth than Voyager 1. If those tests went well, the team could attempt the same fix on Voyager 1 no sooner than July. Notice what that means. Voyager 2 is not only fighting for itself, it is also becoming the proving ground for its twin's next chance. If that power-saving strategy works, the reward is not abstract. It buys time for real measurements. The magnetometer can keep tracking the magnetic field beyond the heliosphere. The plasma wave subsystem can keep listening to disturbances in interstellar plasma. These are not leftover scraps of science. They are the only direct readings we have from that region. Every extra month matters because there is no second spacecraft beside Voyager 2 to check its homework. The beauty of this science is that it can connect the cosmic and the ordinary in one breath. Plasma waves are vibrations in electrically charged gas. Magnetic fields are invisible structures that shape how particles move. You cannot see either one in your kitchen, but you live inside their larger story. Earth rides inside the heliosphere. The sun's bubble shields us from part of the harsher environment between stars. When Voyager 2 samples that outside region, it is telling us something about the boundary of our home. That boundary is not simple. Voyager 2's measurements helped confirm that the heliosphere is not a neat sphere. NASA has described it as squashed or dented. That matters because the shape of the heliosphere affects how solar wind pushes out and how interstellar material presses back. It is the difference between imagining your neighborhood as a perfect bubble and learning it is a weather-beaten shelter pressed by an outside storm. And there are still open questions. How does that boundary change over time? How do pressure fronts move through interstellar space? How stable are the magnetic conditions around the spacecraft? Even when scientists feel confident about the broad picture, the details stay lively. That is why Linda Spilker's warning matters so much. Any day could be the last. Any day could also bring another clue that forces a small rewrite of what we thought we knew. There is also the human system on Earth, which deserves its own share of wonder. The Deep Space Network is not a movie prop. It is a real, global communication system. And for Voyager, the Canberra dish known as DSS-43 carries a special burden because it is the only antenna powerful enough to send commands to the probes. When that dish went offline for upgrades from May 2025 through much of February 2026, the mission had to prepare in advance, knowing long periods of silence were coming. That dependence creates a deeply modern kind of suspense. Not a pilot gripping controls, but engineers planning months ahead because one antenna on one continent will be down. The household version is easy to feel. It is like knowing your only locksmith will leave town for half a year, so you test every old key before he goes. Except these keys are radio commands, and the lock sits past the edge of the sun's magnetic bubble. By late 2026, the numbers grow even more precise, and precision itself becomes emotional. NASA says Voyager 1 is expected to reach 1 light day from Earth on Wednesday, November 18th, 2026, at 2:16:07 a.m. Pacific Time. Voyager 2 will trail behind, but it remains one of only two human-made objects operating beyond the heliosphere. The point of a number like that is not just scale, it is intimacy. You can circle a date. You can picture the signal needing a full day to cross. The older the spacecraft gets, the more every digit feels heavy. More than 13 billion miles from Earth, roughly 21 billion kilometers, about 19 and a half hours for a command to arrive, about 4 watts of power lost each year. 7 of the original instrument systems already shut off. These are not just facts. They are the pressure marks of time. They show how thin the edge has become, and why a tiny maneuver can feel more dangerous than a roaring launch. And yet the mission is not only about avoiding death, it is about squeezing meaning out of the time that remains. Patrick Keane said the extra data are a testament to the engineering behind Voyager. That is true, but it is also a testament to restraint. The team keeps choosing what not to do, so the spacecraft can keep doing what only it can do. There is wisdom in that. Sometimes survival is subtraction in service of wonder. So what should you watch for next? Watch the instrument status. Watch for any note about another planned shutdown on Voyager 2. Watch for updates on power-saving changes and heater management. Watch for any sign that the remaining instruments continue sending back clean data. The next great Voyager news may not come as a giant discovery headline. It may arrive as a modest engineering update that quietly buys another year in the dark. Bring it all the way back to your own life. Somewhere tonight you may charge a phone, turn off a lamp, or listen to a faint sound through cheap earbuds. Those are ordinary acts. Voyager 2 turns ordinary acts into a survival strategy across interstellar space. Power, aim, heat, patience. The cosmic story rests on things so basic they almost disappear. Maybe that is why it feels so moving. The farthest machine we have still lives by the same rule we do. Resources matter. What comes next will almost certainly be quieter than the past, but not smaller. Another instrument may go dark. Another clever workaround may buy a little more time. Another unexpected fluctuation may force NASA to act before a fault protection system acts for them. The drama now lives in margins and timing. That can sound less exciting than a planet flyby until you realize the stakes. We are trying to hold open a listening post between the stars with the last good watts of an aging machine. Sooner or later, one of the Voyagers will send a final useful data set. Then maybe only engineering tones. Then maybe nothing. But until that day, every returning packet is proof that distance has not won yet. Every signal says the spacecraft still knows where Earth is. It still remembers the guide star. It still has enough warmth in the lines. It still has a voice, however thin. And tomorrow, or next month, or on some date now buried in a mission calendar, someone at JPL will open a new stream of numbers and see either relief or trouble. That is the horizon now. Not a new planet rising in frame, but a new decision about what to save, what to switch off, and what tiny chance to take. Voyager 2 has turned the future into a series of whispered engineering judgments, each one carrying the weight of a world. The larger promise in all of this is not that old machines last forever. They do not. The promise is that careful minds can keep discovery alive long after spectacle fades. That matters for future probes, future telescopes, and maybe even future human journeys farther out. If we learn how to nurse fragile explorers through their old age, we do not just honor the past. We widen the map for whatever comes next. So hold one image as we close. Not Neptune, not launch. Picture a faint radio tone leaving a dish on Earth, sliding into space for 19 and a half hours, reaching a craft more than 13 billion miles away, nudging a tiny system inside it, and then waiting another long stretch for the answer. No cheering crowd hears that moment. No bright flame marks it. But whole chapters of human knowledge can depend on whether that whisper works. Save November 18th, 2026, or simply bookmark this story and come back to Voyager updates the next time the mission speaks. That quiet habit pays you back with a rare feeling most people never get, the sense of watching the frontier move in real time. Because the future of Voyager 2 is not really a story about decline. It is a story about attention. As long as engineers can still listen, still calculate, still dare one more careful fix, the spacecraft remains more than surviving metal. It remains a bridge. And one day, when its voice finally stops, it will not feel like the end of an old machine. It will feel like the night a very distant lighthouse went dark after showing us, for far longer than anyone expected, where the edge of home really is.